Nothing. Hello, everybody. Today's speaker is Hans-Christoph Grunau from the University of Magdeburg, and he will talk about boundary value problems for the Willmore and the Helfrich functional for surfaces of revolution. Please take it away.
Thank you very much. I'm grateful to you and also to Philipp Reiter, Guofeng Wang, and Simon Blatt for the kind invitation and the opportunity to give this lecture tonight. Now I should share the screen. Okay, is this fine for you now, for everybody? Perfect. Okay, that's what you already know. That's the title. That's my name. Next thing is my co-authors. First of all, Anna Dall'Acqua and Klaus Deckelnick. I don't think that I need to introduce them. Next one is Marco Doemeland. He was a master's student of mine 3 years ago. He wrote a very, very good master's thesis, and afterwards we developed this to a publication. Then he moved to Aachen. I guess some of the organizers know about the importance of the Rheinisch-Westfälische Technische Hochschule in Aachen. There he received just a couple of months ago his PhD degree. The first co-author is Sascha Eichmann. He's now in Tübingen. He was so far my best PhD student. He received a very good grade for his PhD thesis, and also this was somehow related to what I'm going to report on. And after his PhD, he moved to Tübingen to become an expert also in geometric measure theory. And last but not least, 3 years ago, I visited Shinya Okabe at Tohoku University in Sendai, and he is also co-author of the last thing I want to mention. The goal of my lecture will be to give an overview of what V6 have found about surfaces of revolution related to the Willmore functional. To start with, let me collect some definitions and some notation. So the Willmore and the Helfrich functional for sufficiently smooth surfaces, so this is really two-dimensional, in R3 embedded with boundary not empty, we define the Helfrich functional h epsilon of s as a Willmore functional integral h squared plus epsilon times the surface functional, the surface area functional, where epsilon is greater than or equal 0. To make the convention clear, h is a mean value of the principal curvatures, and as I mentioned, for epsilon equals 0, we call h naught of s, also w of s, the Willmore functional. Smooth critical points of the Helfrich functional are called Helfrich surfaces and called the Helfrich equation, that is the Laplace-Beltrami on the surface of the mean curvature plus 2 times h squared minus k, the Gaussian curvature, minus 2 epsilon h equals 0 on the surface we are looking for. This is a quasi-linear fourth order elliptic equation, but it's not uniformly elliptic. So there are two bad news. First of all, non-uniform ellipticity, but if it were second order, people know by now how to deal with that. But it's also a fourth order, and there are also well-known, well-established tools from second order theory, in particular maximum principle-based tools, do not work. So it's not completely obvious how to tackle the variational problems, how to solve this differential equations subject to boundary conditions. I like working on boundary value problems, in particular on the Dirichlet problem, and the task is find Helfrich immersions S, or if possible, even better, Helfrich minimizes S such that the boundary ds is prescribed and fixed, and not only the boundary, but also the tangential half planes along ds are prescribed as well. In the Helfrich functional, maybe you missed the Gaussian curvature, which is a product of the principal curvatures, but since I'm working with Dirichlet boundary conditions, this is nothing but a constant. by a kind of Gauss-Bonnet formula, and it may be dropped. So it's not the most general Helfrich functional, but adding the surface area adds some significant degree of difficulty. For this general setting, let me mention a couple of important existence results. First of all, the first one solving the Dirichlet problem in this general setting was Rainer Schätzle, the Willmore boundary problem, already 11 years ago, and appeared in the Calculus of Variations, PDE. And not really a surprise, he used a geometric measure theoretic approach, and he finds branched Willmore minimizers for the case epsilon equals 0 in the compactified R3, so in R3 union infinity. He did not deduce any kind of a priori bound, and the minimizers he found may even contain the point infinity. After Sascha Eichmann moved to Tübingen, he wrote a somehow similar subsequent paper to Rainer Schätzle's on the Helfrich boundary value problem, appeared in the same journal, but 9 years later, again, Sascha Eichmann used the geometric measure theoretic approach, but for epsilon strictly positive, the situation is slightly better because there one has area and subsequently also diameter bounds. But also he finds branched Helfrich minimizers, but since they have bounded diameter, he can find them in R3. And there is this somehow competing paper to Sascha Eichmann's by Francesca da Lio, Francesco Palmorella, I guess he is in the audience, and Tristan Rivière, a resolution of the Poisson problem for elastic plates, a recent paper having appeared in the archive of rational mechanics and analysis. It's somehow related to the Eichmann paper, not precisely because I think they prescribe the area and then look for Willmore minimizers, but up to calculating Lagrange multiplier, I think it's more or less the Helfrich boundary value problem. Again, here you have area and diameter bounds, but their approach is not geometric measure theoretic, but somehow more classical. It's a parametric approach. In general, because the framework is completely general, you will have little geometric information, and that's also not the aim of these papers. These solutions may not be embedded, but there are certain criteria that they are embedded, but in general, they will not be global graphs. What my friends and I did in the past 12 years is completely different. We did not aim at generality, but at precise and concrete geometric information. And for this reason, and maybe also for some lack of competence in geometric measure theory, we decided to stick to surfaces of revolution. So we tried and succeeded in finding solutions, or better minimizers, where we have and can uncover more precise geometric information. To this end, we work in the class of surfaces of revolution. So U of x is a profile curve as smooth as we need it, and the surface of revolution is then given by the graph of ux, comma u of x, and then rotated around the x-axis. So x, u of x cosine phi, u of x sine phi. X is over the prototype interval -1, 1, but thanks to scaling, this is not of importance, just for convenience. And the rotating angle phi is in the interval 0 to pi. And we prescribe Dirichlet boundary conditions. In general, they need not be equal. So u at -1 equal to alpha and u of 1 equal to beta, and a horizontal clamping that is u prime of ±1 is equal to 0. I would say this problem is 1.5 dimensional because the analysis is still 1 dimensional, and we may apply gluing techniques, and I will show 2 or 3 examples of this. And this technique is exactly what is missing in the 2-dimensional framework. So you don't have a maximum principle, everybody knows that, but it's also not clear if you don't have symmetry, how to glue in better surfaces. And in 1D, we could so long, in many, many cases, succeed in finding substitutes, how to improve minimizing sequences, how to improve potential minimizers. And since we may apply these gluing techniques, we can obtain sufficiently strong compactness. On the other hand, the geometry is already 2-dimensional because you have 2 competing curvatures, and I will explain in a minute how they work against each other, and you will already see some interesting phenomena. As I claimed, the geometry is already 2-dimensional, and for convenience, maybe you are not working every day on surfaces of revolution. I give here the formula for the mean curvature. So this term is a curvature of the profile curve, u double prime over 1 plus u prime squared to the 3/2 with a minus sign, so that the ball has a positive curvature, but then you have also the curvature due to the rotation, 1 over u times the square root of plus 1 u prime squared. And now I write in full detail the Helfrich functional with parameter epsilon. So it's 2 pi, the integration over phi is easily carried out because nothing depends on that. Integral from -1 to 1, h squared, and this is a surface element, u of x times 1 plus u prime squared, plus 2 pi times epsilon, integral from -1 to 1, u of x square root of 1 plus u prime squared. And this is the surface integral, the surface area. And thanks to the boundary condition, I can multiply, I can calculate this squared term by term, and the mixed term is just the boundary term and can be dropped. So I have pi half, the first term squared, u double prime squared times u over 1 plus u prime squared to the 5/2. The second term, the other way around, the first term squared times the area element, it's pi half times the integral from -1 to 1, 1 over u square root of 1 plus u prime squared, and then the area integral, just integral over u times 1 plus square root of 1 plus u prime squared. And I think already from giving a look at this, you see that at least these 2 terms are competing with each other because they are just reciprocal to each other. But let me go in some more detail. So this term dislikes large u, this term enjoys large u, this term dislikes large u. This term likes very much vertical lines. This term does either, but this term dislikes vertical lines. Yeah, and already it's not only that these terms work against each other, but also these terms work against each other. So there is no obvious trick, say by reflection, how to decrease the Willmore energy. For instance, if you reflect along a line so that u double prime and u prime remain the same, you, for instance, decrease u. This is nice here, but bad here. So standard reflection techniques will not work. And that's what I write here. There's no obvious trick how to improve a given minimizing sequence and how to gain a priori geometric information. Okay. Yeah, and at the end, we did not really work analytically because working purely analytically, it seems more or less important to gain control of all these 3 terms. All the reasoning more or less was geometric. The next 20 or 30 minutes, I will deal with a pure Willmore functional that is with epsilon equal to 0. This is joint work with Anna Dall'Acqua and Klaus Deckelnick. And again, this makes things much more easy. We look first at the symmetric case, alpha equals beta. I recall the parameterization of the surface of revolution. U of x is a strictly positive, sufficiently smooth profile curve rotated around the x-axis. So x phi is mapped onto x, u of x cosine phi, u of x sine phi for x over minus 1, 1, and phi in 2 pi. And here we have a theorem which at the first glance, and when it appeared, was quite surprising, in particular to experts in minimal surfaces. For all positive epsilon, there exists a C infinity smooth profile curve, strictly positive, such that the corresponding surface of revolution solves the Willmore equation over minus 1, 1, and attains the Dirichlet boundary data u of plus minus 1 equals alpha and u prime of plus minus 1 equals 0. U is even, and in this class minimizing, and moreover we have that for all x in 0, 1, u prime is decreasing, so the shape of the graph is bending upwards first and then downwards at the end. And moreover, this is a certain information which will prevent the graph from becoming too large, and the meaning will be explained in a couple of minutes. X plus u primed is always greater than or equal 0 for all x in the right half of the interval. And as you can easily see from these geometric properties, this means that we can compare it with a circle. So u of x is bounded from above by the circle square root of 1 plus alpha squared minus x squared, and from below by this property by alpha. And once you have this here and bound from below, u prime of x is bounded from above by 1 over alpha. And the goal is to find good minimizing sequences which have exactly these properties. And then you have C1 compactness, 1, you have C boundedness. You immediately have for minimizing sequences also H2 boundedness. The Willmore functional is more or less qualitatively linear. So you have weak H2 convergence, strong C1 convergence, and that is by far more than you need to pass to the limit. But how to single out suitable minimizing surfaces? At the end, after we understood everything, we could have done everything in the Euclidean setting, but to understand what's going on, it was quite useful that Ernst Kuwert mentioned to me work from the 1980s by Bryant, Griffiths, Pinkel, Langer, and Singer. And Langer and Singer was very, very important also for Sascha Eichmann. So the profile curve lives in the upper half plane, y greater than 0. And if you equip this with the hyperbolic metric, that is ds squared is 1 over y squared times the Euclidean metric, you can calculate the hyperbolic curvature as follows. It's a sum of the fraction u double prime over 1 plus u prime squared to the 3/2 plus 1 over the square root of 1 plus u prime squared. And if you remember the expression for the mean curvature, you just need to take this one and put it here. Oops. Put it here and put a minus sign here. So there is some formal similarity, and thanks to the boundary conditions, the mixed term is of no importance. And thanks to the different character of the hyperbolic line element, I mentioned this thanks to the boundary condition, we have that the hyperbolic bending energy, that is the integral from -1 to 1, the hyperbolic curvature squared integrated with respect to the hyperbolic line element is nothing but 2 over pi times the Willmore energy of the surface of revolution. And now it becomes clear why spheres are preferred by the Willmore functional, because spheres, that is circles centered at the origin, rotated around the x-axis, are hyperbolic geodesics. So there is no hyperbolic curvature, and also vertical lines are perfect for the Willmore function. These we do not really like, but the circles are perfect for our purposes. And I can explain at least one argument how to improve minimizing sequences. So we define for the given boundary datum alpha in 0 infinity the class of competing functions C11. So first derivative is Lipschitz over the prototype interval minus 1, 1 with values in 0 infinity. V is even, and V attains the Dirichlet condition alpha, and V prime of 1 is equal to 0. And the important result, the most important step to achieve the existence result I mentioned before, is that we may achieve a minimizing sequence V alpha k in N alpha such that it has this property, that is on the right interval, half interval, it's decreasing. That means on the left, it's increasing. And this was the most difficult property to understand. And x plus v, v prime is greater than or equal 0. And as I mentioned, once you have these properties, you have C1 bounds on the minimizing sequence, then you have H2 compactness, you find a minimum, and then you can easily see that's C infinity smooth. Now I want to explain how to suitably modify minimizing sequences. Assume that we already understood that it is better, and this is by no means obvious. There is no reflection trick. That was really tricky to understand why this is preferred by minimizing sequences. So decreasing on the right half interval, increasing by symmetry on the left half, and assume that that was already achieved, How can we also achieve that for all x in 0, 1, we have x plus v, v prime is greater than or equal 0. And the proof is just by drawing a picture. So assume that at the first instance, this was your vk. And what is the meaning of x plus v, v prime? This has the following meaning: go to the point x and draw something orthogonal in the point x, v of x, and then take a Euclidean straight line, and then the intersection of this straight line with the x-axis, this is precisely x plus v of x, v prime of x. So if x is here, x plus v, v prime of x is here. And assume, as I draw it here, that this intersection point, here of course it is far away from 0, becomes sometime at the first instance equal to 0. Because we are working in a symmetric class, we have the same picture on the left hand, on the left part of the interval, and we can immediately insert this geodesic arc. So whatever you have to pay for this, it is for sure more than 0, and the element of the minimizing sequence becomes cheaper for the Willmore energy if we replace, in case that this becomes 0 somewhere, if we replace the original graph by the circular arc. And then we have ensured that this holds true forever. Okay, this is one gluing argument. Applying such kind of gluing argument becomes already much more difficult when we do not have this symmetric situation. So for instance, when we deal with unsymmetric boundary data still in the framework of surfaces of revolution. Okay, here are some pictures, numerical pictures provided by Friedhelm Schivek from my university. And here you see that the minimizers obtained numerically look pretty much like what I drew before. And in fact, there was a very intense interplay between the numerical guys and the analytical guys, Anna, Klaus, and me. And if you go down with alpha very close to 0, you see, oh, it looks pretty much like a circle. But then if you zoom in, what's that? That's for sure not a circle, because we still have the Dirichlet boundary conditions here. But you may guess what this is. And that we have solutions and are even able to compute solutions numerically for alpha almost equal to 0. That was at the beginning a surprise, in particular, and not only to numerical guys, but also to analytical guys, because from minimal surfaces of revolution, you know, there is some boundary data over the interval -1, it's 1.5 or so, below which you don't have any minimal surface of revolution. And here you have them up to alpha or down to alpha almost equal to 0. And also the numerics does not really become unstable, but of course you need some intuition how to construct some initial value to start the gradient flow algorithm. And of course, if you switch back from the hyperbolic functional to the original functional, you may have an idea what could be a good guess to attain the Dirichlet data on the left and on the right. And that is exactly what I want to explain now.
May I ask a question?
Sure.
To that point. So is this one the catenoid?
Yeah, that's exactly correct. Thank you so much, Gurufang. That's exactly.
Okay.
So at the beginning, intuitively, we constructed the initial data by putting a catenoid here and there, and then push a circle from below such that it touches the two catenoids. That was our intuitive guess, and that worked perfectly with the numerics, because the catenoid is, of course, what is preferred by the original Willmore functional. And a couple of years later, I thought I would like to prove this rigorously. So for alpha small enough, let U alpha and N alpha minimize the Willmore functional in this class, then looking from the point x equals 1. So I calculate the difference between x and 1. I scale it by alpha. I subtract it from 1. And then I divide by alpha. So in some sense, I consider x equals 1 as a new origin, and I multiply the original graph by 1 over alpha. And then I can prove the limit for alpha going to 0 is precisely the cosh of 1 minus x. And this is smoothly convergent on 0, 1, or even on some fixed interval larger from some minus fixed negative point to 1. And in this sense, if you solve for U alpha of x is asymptotically equal to the catenoid, which is exactly the answer to Gurufang's question, alpha times cosh of 1 minus x over alpha on the boundary layer 1 minus alpha to alpha. And for any epsilon strictly positive on some slightly smaller intervals, so there is some transition layer. So, but up from 0 to 1 minus alpha to some power slightly smaller than 1, U alpha of x is asymptotically equal to 1 minus x squared. And here you have smooth convergence. So in the interior, you really see the circle, and on the boundary layer, 1 minus alpha to alpha, you see after rescaling the catenoid. So these are the two prototypes which you want to see if you minimize the Willmore functional, and they become more or less evident for very small boundary data. I cannot give the full proof here. Again, there are some technical issues, but I want to explain one lemma which is important. So this is another bound from above. So the minimizer of the Willmore functional is always below the catenoid, which we put on the right boundary suitably rescaled. So the catenoid is always above the minimizer of the Willmore functional. And again, this is explained by giving a picture. So the red line is the minimizer. This is U alpha, and the green line is a catenoid. And assume that the catenoid lies on some interval below U alpha. Then the idea was to look at these functions not as graphs over X, but as graphs over the angular rays, so as functions in phi. So I let this ray move as a function of phi, and I take the intersection points. And as a function of phi, I go to the point where the distance of the catenoid and the Willmore functional becomes maximal. And then the two tangents are parallel, and then I can rescale the Willmore minimizer. I can put it in here as I drew it here, and then I have here the original energy. I should have mentioned, but I think you are all experts. The Willmore function is scaling invariant, so the Willmore energy does not change if you multiply some geometric object by some factor. So this part of the Willmore energy is exactly the same as for this part, and here it's for free. Here it's a catenoid, here you pay nothing. And since the original minimizer was not a catenoid, here you had to pay something for the Willmore energy. Here you do not pay anything. So this would have strictly lower Willmore energy than the original Willmore minimizer. And to strictly decrease the Willmore energy of a Willmore minimizer, this does not work. So it cannot happen that the cosh is somewhere below the Willmore minimizer. This is one argument, but this seems to be quite important also what I'm going to work on right now, the framework of Helfrich functional. Okay, this is just one glimpse on one lemma, on the proof of one lemma for this asymptotic result. I want to mention further works on surfaces of revolution. First of all, Anna Dall'Acqua, myself, Steffen Fröhlich, and Friedhelm Schewek for the numerical part. We could deal in the symmetric setting with arbitrary boundary angles. Sascha Eichmann, I mentioned, an excellent PhD student. I think he received his degree 4 years ago. He proved that the boundary value problem has more than one solution. So non-uniqueness of solutions of the boundary value problem. It's still open whether one has uniqueness of the minimizer, but for solutions of the boundary value problem, for sure, you have non-uniqueness. And he proved this by having really understood this seminal work by Lange and Singer. There you are not really sure, is this geometric intuition or is it proven analytically? And half of that was proved analytically by Sascha Eichmann, other half of this that was proved by Rainer Mandl. So in this work, which appeared in the Annals of Geometric Global Analysis and Geometry, AGAG, he provides any possible explicit formula for surfaces of revolution. So for minimizers or curves in the hyperbolic half plane. But back to Sascha Eichmann, joining Amos Köller before he went to Tübingen. Amos Köller was at that time a PhD student, now a postdoc, in the group of Rainer Schätzle, and they could prove that minimizers are symmetric with respect to X. So surfaces of revolution which minimize the Willmore functional have a symmetric profile curve. This sounds pretty much like uniqueness of the minimizer, but it's not sufficient. It still may happen that there are two symmetric minimizers which intersect each other, and so far I haven't found an argument, but perhaps this will happen within the next couple of years. if you drop the Dirichlet boundary conditions and you stick to natural boundary conditions, so you simply cross this out in your class of admissible functions, things become somehow simpler. So in the symmetric setting, Bergner, Dall'Acqua, and Fröhlich proved existence of Willmore minimizers also for small alpha. They look different from what I showed you before. They look somehow like catenoids, but of course they cannot be catenoids. But the lower part of the Clifford torus is for some value of alpha, I think it's alpha equal to 1, is this minimizer, and they can extend this branch down to alpha equals 0. And this branch of non-trivial Willmore minimizes crosses the two-fold branch of catenoids, and Klaus and myself could prove that this intersection point is in fact a bifurcation point. So you will, this Willmore minimizers will persist, but as unstable Willmore surfaces, which are not catenoids. And Dall'Acqua, Deckelnick, and Glenn Wheeler, a Humboldt fellow at that time, could prove that this branch could be extended for any alpha beyond this 1.59 to infinity, and you have unstable Willmore surfaces. And I find this a really important work, because at the first glance you would think of applying some kind of mountain pass theorem, but it's more or less impossible to verify the Palais-Smale condition for this functional. And they could really bypass using the mountain pass lemma. Instead, they used that we could solve for any boundary condition the Willmore problem, and they found by a kind of Bolshajev-Noether identity that for certain angles you also have that the mean curvature becomes equal to 0. And so for sure, these are not minimizers. They are somehow unstable, but they are not obtained by using the mountain pass lemma. And I guess nobody has been so long been able to calculate the Morse index of these solutions, but I guess the Morse index should be 1, but it's just a conjecture. Now let me briefly explain the non-symmetric case, alpha, which is now the boundary datum u of -1 equals alpha, beta, the boundary condition for u of 1. Again, under natural boundary conditions, also by Bergner, Dall'Acqua, Fröhlich, could be solved much more easily for any set of alpha and beta. But if we want to work with the Dirichlet conditions with horizontal clamping, we need to assume a kind of smallness condition. So again, the sphere and the catenoid play an important role, and the condition is that the catenoid we put at the left boundary condition is always above the circle we put at the right boundary condition. So here is alpha, here is beta. And beta should be large enough, so always below alpha, but large enough that the catenoid and the circle do not intersect. And then there exists a smooth graph such that the corresponding surface of revolution solves the Willmore equation over -1, 1, and u of -1 is equal to alpha, u of 1 is equal to beta, and u prime of +(-1) is equal to 0. Moreover, u minus the Willmore function in the class of all smooth curves over -1, 1 from -1 alpha to 1 beta with horizontal slope in these points. So it's optimal to be a graph if this smallness condition is satisfied. And maybe this is also interesting for people who prefer not to work with graphs because it's somehow a claim about geometric simplicity. So the profile curves become geometrically simple if this smallness condition here is satisfied. They become projectable onto the axis of revolution. The smallness condition, maybe not in this form, but in some form, is necessary if the difference between left and right boundary datum is too large, and if we stick to horizontal clamping, the minimizer looks like that. This is calculated numerically by Sascha Eichmann. But I expected that also analytically, and if you decrease the right boundary datum, this vertical path moves to the right, and if you think this would persist a while longer, then you can prove that a kind of gluing technique becomes applicable. And that is exactly what Sascha, Eichmann, and myself did. First, we proved that there is a Willmore minimizing curve, which at the first instance is not necessarily projectable, but obeys boundary conditions. Here, energy arguments, which will be explained later, are quite useful. The proof of projectability is by contradiction, and here explicit analysis of the curvature equation and of the accompanying killing field introduced by Lange and Singer was quite important. It was essential. I had long time ago the idea how to improve minimizing sequences, but I could not ensure that we always have a situation where such a kind of gluing technique would be applicable. And it was the contribution, the most important contribution by Sascha Eichmann, that he could prove by this very technical analysis that in fact, if the smallness condition I mentioned before is satisfied, then we have a situation where we could glue in from the left a cosh, from the right a circle. The cosh could be moved along the potential minimizer, and then we would have something cheaper. And so the original minimizer were not a minimizer, but there is something projectable, which is minimizing. Now let me come to the Helfrich functional. So from now on, epsilon is strictly positive, but here we have results only for the symmetric case, alpha equals beta, and this is joint work with Klaus Deckelnick and Marco Doemeland, who received his PhD, as just mentioned, at the important place of Aachen. At least for a relevant part of the audience, I think this is the most important place mathematically. And here is an overview of for which kind or in which range of parameters we have existence of minimizers. First of all, there is a cylinder. So the vertical line, and for epsilon equals 1/4 alpha squared, this is the absolute minimizer of the Willmore functional. We performed perturbation analysis, the implicit function theorem, and so we have a small neighborhood around these Helfrich cylinders where we have existence. And we could also calculate the profile of the rate of change function. And so we know when when epsilon comes from below, at least in a certain range, the minimizer is above. And if we pass beyond epsilon equals 1/4 alpha squared, the minimizer is below. But the profile of the rate of change function is of this simple shape only for alpha above a certain threshold, 0.18, and below the rate of change function becomes oscillatory. It oscillates, it's still positive, but it becomes oscillatory. And that's what we often observe in fourth order equations. You have somehow an idea how a minimizer should look like, but then you have overshoot and undershoot and again overshoot. You're oscillating around the expected optimal curve. And you can really observe this, and this is rigorous analysis in a small in the range of very small alpha. So this is maybe interesting, but not what I will focus on. Sebastian Scholtes, again, a student of Heiko von der Mosel, like at least 3 of you, wrote his diploma thesis at that time, and he found this region of existence here. Marco Doemeland found the blue regions in his master's thesis. This is by energy tricks. But so far we had no region or no parameters alpha where we had existence for any epsilon greater than or equal to 0. And that is a main contribution, in my opinion, for alpha m above 1.8995. We have existence for all positive epsilon. And again, there are experts in minimal surfaces. And what is a guess? What is this value? What is the meaning of this value? 1.895 ... If you think of surfaces of revolution, you have catenoids from 1.59 ... on, but for alpha in this range, they are not energy surface minimizing. So there's still the Goldschmidt curve, zack, 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 has smaller area than the catenoids. And from this value on, the larger catenoid, which has a larger central value, is an absolute area minimizer. And this is really important for us in order to be able to apply a kind of gluing technique again here. But first of all, I want to explain the energy trick. So as before, an alpha is a usual class of admissible functions, C11, differentiable and first derivative Lipschitz, even attaining the boundary condition, and assume that you can show that the minimum of your Willmore functional is below 4 pi. So you know the minimum of the Helfrich functional, but if you can deduce from this that the Willmore functional on the minimizing sequence is below 4 pi, then we have an estimate for V prime, namely by the Willmore energy of V over the square root of 16 pi squared minus Willmore energy of V squared. Okay, we choose a point where V prime is maximal, and we assume that V prime is negative, x naught is positive, so that the function V looks somehow like this. It's increasing somewhere on -1, 1. It's decreasing somewhere on 0, 1. And now we work with the original Willmore functional, and the idea is going from 0 to something very steep, going to something very steep but decreasing to 0. This could be achieved by a catenoid. This will be not expensive, but going from something very steep, increasing to something steep, decreasing, this will cost Euclidean Willmore energy. So we throw away the Willmore energy from -1 to -x naught and from x naught to 1. That's what I write here. This is a surface element, and now we take the plus instead of the minus sign. We have to balance this mistake by -2 pi times V prime over 1 plus V prime squared, evaluated at x naught and minus x naught. If you look at the product of this, this is nothing but V double prime over 1 plus V prime squared to the 3/2. And this is exactly the primitive of this integrand. So here we don't throw away, because we are interested in what's going on at x naught. We don't throw away the mixed term, but we throw away all the positive terms, and we end up with an estimate from below by 4 pi times the modulus of V prime over the square root of 1 plus V prime squared. And now, if this is strictly below 4 pi, this cannot become infinitely large. As soon as this is below 4 pi, you have an upper bound for the derivatives. And this is a trick how to prove existence in the blue regions I showed you before. So this explains one argument how to achieve existence in the blue regions. But now I want to stick to the purple region. And as I mentioned, alpha m is Cm times cosh 1 over Cm. And Cm solves some equation. And for alpha greater than or equal alpha m, the equation C times cosh 1 over C equal to alpha has three solutions: a larger one, C1 of alpha, a smaller one, C2 of alpha, and V alpha defined as C1 alpha times cosh x over C1 alpha is a global minimizer of the area functional. absolute minimizer of the area functional. And the theorem now existence via gluing techniques for alpha greater than or equal this alpha m and epsilon greater than or equal, yeah, we would have enjoyed 1 over 4 alpha squared here, but we need to take the boundary data of V alpha. Now the central values, not the alpha would have been the boundary values of this catenoid, but we have to take the central values. 1 over 4 times the minimum of V alpha squared. V alpha are the area minimizing catenoids. The Helfrich functional admits a minimizer in n alpha, and this satisfies the derivative is always positive and smaller, strictly smaller than the derivative of V alpha. U alpha is always strictly below alpha and strictly above the area minimizing catenoid for large enough epsilon. So we can rigorously prove that for sufficiently large epsilon, the Helfrich minimizer becomes somehow catenoid-like, catenoid-shaped. And one more gluing trick for U in an alpha, there exists a modified function V in an alpha such that the derivative of V is strictly less than the derivative of the area minimizing catenoid, and we do not increase the Helfrich energy. And in particular, we have that V is above the area minimizing catenoid. So we immediately find a bound from below for suitably modified minimizing sequences. And again, the proof is by drawing a picture. So this here is the area minimizing catenoid. And assume that you have some element U of a minimizing sequence, which is somewhere steeper than V, but at the end it must become flatter. So there's some x naught where the slope of U is exactly the slope of V alpha. And okay, now I increase this V alpha. So I increase the central value. The C1 of alpha is increased. C becomes larger and larger and larger. So the area minimizing catenoid becomes flatter and flatter. And so here you would have a transversal intersection. So you have to increase further. And then there will be a situation where the catenoid just touches the original U. And then you take the original U here, the original U there, and you take the area minimizing catenoid. This is not steeper than this one here. And so you have something which is flatter, at least as long as you are increasing, and has less Willmore energy because the mean curvature is equal to 0. So you cannot have something cheaper as for the Willmore energy, and from here to there, you cannot have something cheaper also for the area functional. Okay, this is the gluing trick here, and the asymptotic behavior, epsilon going to infinity, takes the family of minimizers which I have just constructed and let epsilon go to infinity, then epsilon goes to V alpha uniformly minus 1, 1, but not smoothly, because the limit is a singular one, because if you multiply by 1 over epsilon, the area function becomes dominating, but the Willmore function will become less and less important, and it disappears. So you pass from a functional of order 2 to a functional of order 1. And I call this a singular limit, and the price you have to pay is that you lose one boundary condition. Okay. In principle, my time is over. I can just stop here, but if you don't mind, it's another 3 slides. I could make a few remarks on the obstacle problem. What do you think?
Maybe 2 to 3 minutes, okay?
Okay. So I just mentioned I have worked with Shinya Okabe on the obstacle problem. I just show the pictures, okay? I show some admissible obstacles. Here we want to, you remember the original shape of minimizers. They want to go bend upwards. Now we want to push the Willmore surface downwards. So I want to put an obstacle here, such the minimizer looks like that. And these are admissible obstacles, slightly enlarged here for these boundary data. So we are able to prove existence if we put, say, an obstacle here of minimizers which look somehow like this, of the Willmore functions, subject to being below this obstacle here. And maybe this is the most interesting example. If alpha is equal to 0.99, I can push it down almost to the origin in the central point. I can put an obstacle here, and this is more or less the shape of the minimizer. And as you easily recognize, we just interchange the asymptotic shape of the minimizers before. Now the circles are here and the cosh is here. It's somehow related to what I did before. When alpha becomes smaller, we can still remember this wants to become the unit circle. We can still push it downwards, but the construction becomes more involved. So circle here, cosh here, circle here, cosh here, circle there, circle, cosh, circle. These are still admissible obstacles, but when alpha tends to infinity, admissible obstacles become more and more boring, more and more equal to the straight line. And here I have a high energy result for large boundary data. Usually one wants to have something below 4 pi. If you look at this here, this is more or less behaving like alpha. So we can prove for large alpha, if the Willmore energy here is below pi times alpha, asymptotically, or a factor slightly smaller than pi times alpha, then we have a minimizer. So these are high energy solutions. And for large alpha, I can push the minimizer below alpha uniformly by something about 0.3, uniformly in alpha to infinity. Maybe geometrically, it's not that impressive, but analytically, it's really impressive because the energy is really, really of the order of alpha. So we are working with more or less infinite Willmore energy and still can prove existence of minimizers, smooth minimizers for the obstacle problem. Yeah, I'm sorry for underestimating the time. I need to explain. I stop here. Thank you very much for attending and for your attention.